Okay, it's January 12th. These are my thoughts about homomorphic encryption. And it's awesome because it allows you to do cloud things on ciphertext instead of plain text. So the idea is like when we have a bunch of data that might be privacy sensitive, how can we use all of our big cloud infrastructure on it? And homomorphic encryption is a classic crypto approach to do that. So you've got like, encryptions that have these properties. And in their strongest property, they're fully homomorphic, meaning you can do operations on them on the ciphertext, and then you can still decrypt it back. When you start digging in, though, it gets squirrely in the sense that, well, there's these little random draws. I put text here if you wanted to like pause. I don't know if anyone's interested like that. But the problem is that there's this trade-off between the security of the encryption method and the number of operations you can do on it in the ciphertext space. And I found what I consider some like iconic or sort of representative works here. So this is 2016's progress. And at this point, they're like doing a very shallow network, but they are doing like MNIST, which is a standardized, benchmark in some computer vision. It's a handwriting recognition. In 2021, though, we're up to CFAR 10, which is 10 different object classes, and they're getting pretty much state-of-the-art recognition among only 10 types of objects. And that's all just giving a cryptographic, like a ciphertext string, and then operating on that, which is pretty impressive. And a lot of deep concessions have to be made to the network. It has to be very shallow. It also can't do classic neural network things, like there's no real numbers in encrypted. It's all like analytic integers. So there's a bunch of like hacking that you have to do to make that work. And it's super compute heavy. You end up having to do 4 hours to tell the difference between 10 classes. So clearly that's not going to scale. And I don't see like an easy way to make that dramatically faster, just due to the fact that you're operating on these like rings of polynomial projections of bits and modulating them, so that's all cryptography, not real number math. Here's a cool one. This one is at the edge, you do feature detection in the sense of like joint angles or key points. Then you put those in, encrypted into the cloud. You do some activity recognition. The idea would be that if you have some camera that's in your house, can someone detect if you have fallen or whatever the application is without having the picture of you in your house? So that's like a classic use case. The problem with these is that you pay a lot for using a cryptographic method, in the sense that a cryptographic method is like an invertible relationship between one string and another string. And that's necessary if your end use case is you want to be able to pull that original string back out. If you have BitLocker or something, you need to be able to get the thing that you encrypted. But there are a bunch of applications where you just need to boil down the application specifics of some data that you're collecting, and you can throw away the privacy sensitive stuff. And so I got to thinking about what that means for non-cryptographic techniques that we've been working on, which is latent space representations. And I'll explain it in 3 quick ways. The first is that you can force neural networks to summarize. And the way you do that is you create layers that they have to go through that are small. And that means that the job of the rest of the layers is to boil down complicated information into simple information. And then on the decoding side, to take simple information and enrich it out to the full space that you care about. The summarized space is called a latent representation. It's like there's something latent underneath that explains everything. And so we've been working on trying to do that better, especially with time varying data. And there's been a lot of interest due to commercial applications in things like images and stuff. But There are tons of other data sources that are actually very difficult because they vary in time. Imagine anything that arises from body motion or anything like that. So we've shown that you can take hand motions, which are, some 20 degrees of freedom, maybe 30, depending on how you're measuring. And you can boil down complex gestures into very simplified 2D planar movements in a plane, or for a full body walking around. And what's important here is that in this latent space, you can see that different things occupy different regions. And that means that you can operate on that latent space to do something like classification. So like on this one, you can see there's stairs and flat ground walking. They occupy different volumes here. So that means that you could just send this location on the plane into the cloud, and then you could have a walking versus stair machine that could be used in an application. And this doesn't have to be 2 dimensions. It can be as many dimensions as you want. It's just the lower you go, the more you're compressing. And the higher you go, the more complicated that space is to work on. Here's an example where individuals appear distinct geometrically. So this could be the opposite of a privacy-preserving representation. And that's what I want to get to next, is that you can preserve or encourage desired properties of these latent spaces. So here's an example that we've been doing, trying to make like a personalized gait simulator. Like, can I capture what's personal about you, or what is it like when you're walking up stairs versus walking up steep stairs, that kind of thing. And so on the left, you've got this bank of attribute-specific encoders. And what's important about those is that they boil down only the attribute they care about, and they're penalized for containing any information that's useful to predict other attributes about. So the way you do that is with these classifiers. And so if an encoder has any information that can be used to guess an attribute that it's not supposed to be encoding, it gets penalized for that. And what that does is it moves the spaces together when it's not supposed to be representing them, and apart when it is supposed to be representing them. And there's like some equilibrium there that you can trade off. So here's an example of how it works. On the left, this is like different people in different colors. If you're just trying to reconstruct people's movements, the people are all jumbled together in the latent space because people are more similar than they are distinct. But here we've got an encouragement to separate people in the latent space while still trying to do reconstruction, and you get people occupying different areas. So you could do the opposite of this to fuzzify the individual while still maintaining a property that you care about, like what activity are they doing, that kind of thing. So I thought this was really exciting, but I'm not the first to think of this. So it turns out that there are already people who are manipulating representations to preserve privacy while still trying to maintain some kind of goal. So here's one where for some reason you want to have facial images that you can put in a representation, but an attacker couldn't reconstruct this private face image. And so that would be like, you're still trying to do what crypto offers, which is like the private party can still completely reconstruct their private data, but the public party can't. Or here's an example of trying to do activity recognition, where you can say, oh, are they walking versus running, but they can't guess the gender. So I want to emphasize, though, that this world of trying to learn representations is one of the hot topics right now in machine learning, and it's nascent. It's just beginning. So if you really have to have encryption, decryption, like you've got to invert back to the original, then these classic number theory crypto methods are required. You have to have homomorphic encryption. But there are a bunch of different applications where what you need is representations. And by manipulating those representations, you could preserve privacy, or you could, you could preserve an arbitrary number of properties that you care about. And so I think that's really interesting, and I think it's an opportunity. And I'm just curious what people think about that. Like, does that align with a need, and is that interesting? I can't tell. Anyway, I just thought I would record it and see what you think. Did I? Oh,